So in today's lecture, we will discuss about inductive sensor, and especially we will discuss about some basic terminologies which we will use in inductive sensor. Basically, this inductive sensor, the working principle of inductive sensor based upon two things. One, it based upon inductor and eddy current. So on the basis of the principle of inductor, on the basis of the principle of eddy current, the working of inductive sensor can be explained. So we will discuss about these things in next lecture, but in today's lecture we will discuss some of the basic terminologies which we use during inductive sensor. Now, first thing is magnetic field lines. Now, what is magnetic field lines? Now, let us assume this is a magnet. This is the south pole of the magnet and this is the north pole of the magnet. So, the magnetic field lines are the invisible lines which comes out from the north pole and which enters in the south pole. So, it will be like this. So it comes out from the north pole and it enters inside the south pole, and inside the magnet it moves from south pole to north pole. See. Inside the magnet moves from south pole to north pole, like this. So outside the magnet, these are the invisible lines which comes out from the north pole and which enters in the south pole. Whereas inside the magnet, these lines move from south pole to north pole. So these invisible lines are called as magnetic field lines. Now these magnetic field lines are unaffected by any non-magnetic material like air, like rubber, plastic, paper, glass. So suppose you place one paper here, paper or glass or rubber, any non-magnetic material. So these material will not give any effect over these magnetic field lines. Now there is another term, magnetic flux. This magnetic flux is denoted by phi. Now the definition of magnetic flux is total number of magnetic field lines which comes out from the north pole is called as magnetic flux. For example, you just see in this particular, we will take this particular case. In this case, this is the north pole. In this north pole, this is the first magnetic field line. This is the second magnetic field line. This is the third magnetic field line. This is the fourth magnetic field line. So in this particular example, total 4 magnetic field lines are coming out from the north pole. So the magnetic flux in this particular case is 4. So magnetic flux is total number of magnetic field lines which comes out from the north pole of any magnet, and it is represented by phi, and the unit of flux is Weber. Right? And it is also written as W V. And 1 Weber is equal to 1 into 10 raised to the power 8 magnetic field lines. So this is about the magnetic flux. The unit of magnetic flux is Weber. 1 Weber is equal to 1 into 10 raised to the power 8 magnetic field lines. So if I say this magnet has a magnetic flux of 1 Weber, this means this magnet has 1 into 10 raised to the power 8 magnetic field lines which are coming out from the north. Now another term is flux density. This flux density is represented by B. Now, flux density is the total number of magnetic field lines which passes through a plane of unit area, provided the plane is placed perpendicular to the magnetic field lines. Now let us assume, suppose now we see, suppose here we place one plane, right? One plane is there. This is, let us assume it is 1 meter by 1 meter. This is 1 square. And this plane is placed perpendicular to these magnetic field lines. So now total number of magnetic field lines which passes through this perpendicular plane is called as flux density B. So this is represented by B and it is given by flux per unit area. Right? Total number of magnetic field lines per unit area, and its unit is Weber per meter square. So this is the unit of flux density. Now magnetic field in a current carrying wire. Suppose we take this wire, so this is one wire. Now we connect one battery to this wire, one voltage source. So with the help of this voltage source, one current will start flowing through this wire. Now one current is flowing through this wire, let us assume this current is I. Now due to the flow of the current, the magnetic field will produce around this wire. So in a current carrying wire, in one straight wire, the magnetic field will be circular type, will be produced, and the magnetic field will be perpendicular to the plane through which the current is flowing. So let us see this case. Suppose this is the wire, and we have connected one voltage source. So current is flowing through this wire, and the direction of current is from top to bottom in this way. So now the magnetic field will produce around this wire, and the magnetic field will be circular like this, right? So in this way you can find the magnetic field is produced here. This circular type of magnetic field will produce. Now this see, the direction of the current is vertical. So the direction of the magnetic field will be horizontal. So the direction of magnetic field produced in the current carrying wire will be perpendicular to the direction of the current. If we keep the wire in this way, and suppose current is flowing through this wire, so wire current is flowing horizontally. So in this case, the magnetic field will be produced vertically in circular form, right? So if this is a straight one single wire, then in that case, circular type of magnetic field will produce. Inductor. Now we can make the inductor by making the turns in a simple wire. For example, like this. Now, suppose this is a simple wire. Now what we will do, we will make the turns in this wire like this. Like this. So this is inductor. So inductor is formed by turning the wires. Now let us assume there are n number of turns. Right? So these turns are, let us assume these are n number of turns. Now see how current is flowing. Now suppose this here, if we connect some voltage source like this, so current will flow from positive to negative terminal like this. It will come here and here. like this. Current will flow through this inductor. Now, due to these turns, the magnetic field or magnetic energy will be stored in the inductor, right? So basically, inductor stores the magnetic energy. So energy is stored in the inductor in the form of magnetic force, magnetic field, right? So now here, so like this. So if this is an inductor, and now in the inductor, the end point of the inductor from where the current enters in the inductor will become north pole. So here, see, since current is flowing through a conductor, this is basically conductor which is having the turns, right? So when the current flows through this inductor, then magnetic field will produce, and the magnetic field will be in such a way, the end of the conductor at which the current enters, so current I enters at this end, so this end will become north pole, and the end of the conductor through which the current comes out will become south. So in this way. So from North Pole, the magnetic field line, these are the magnetic field lines which comes out from the North Pole and which enters in the South Pole, and inside this coil the direction will be from south to north, right? So if we take one inductor and we allow the current pass through that inductor, then magnetic field will produce. That end of the inductor from which current enters will become north pole, and the end from where current comes out will become south pole. Now see here, these are the turns of the coil. Right now, only air is there in between these turns. Now, if we put one magnetic material, right, soft iron type of material here, then due to that material, the intensity, right, of these magnetic field will increase. So we will not go in detail with reference to that, but here you just understand about the inductor. Now with the inductor, now here suppose now in place of this DC source, suppose here I connect one DC source. So now what will happen? When the direction of, now during the positive half cycle, let us assume during the positive half cycle the direction of current is this, and during the negative half cycle the direction of current is this. So this I during negative cycle, this I during positive cycle. So now what will happen? During positive cycle, this is the direction of current, so this end will become north pole of the magnet, and this end will become south pole. During the negative half cycle, the direction of current will be this. So in this case, this end will become north pole and this end will become south pole. So in this way, we can change the these poles of the electromagnet, right? So basically, this is an electromagnet. Due to the flow of the current, the magnetic field is produced. with reference to this inductor, there is Faraday's first law, and the Faraday's first law says that when a conductor is placed in a varying magnetic field, then a voltage is induced in the conductor. What is the meaning of this? Now, suppose this is one conductor and this conductor is placed, this is some magnetic field, right? This conductor is placed in varying magnetic field, then a voltage is induced in this conductor. This is the Faraday's first law. And Faraday's second law says that the induced voltage, we write the induced voltage by V EMF, induced voltage is equal to N d phi by dt, and here there is minus sign. This expression is related to Faraday's second law, and it means that the induced voltage, this is and when the voltage will be induced? When a conductor is placed in a varying magnetic field. So induced voltage is proportional, directly proportional to the number of turns in the coil. And it is directly proportional to rate of change of flux. d phi by dt. Phi is flux. So if we increase these number of turns, then the voltage induced in this coil will increase. Second thing, or if we increase the rate of change of flux, means if we change this rate of, if we change this flux, right? Flux means total number of how much total magnetic field lines which are coming out from the North Pole. So this can be changed by increasing or decreasing the amplitude of this voltage. If you increase the voltage, right? If you increase the voltage, then the number of the magnetic field lines will increase. You decrease the voltage, it will decrease, right? So if the rate of change of flux is more, then more voltage will be induced in this, right? Or if the number of turns in the coil is more, then more voltage will be induced in this coil. And the negative sign, it indicates that the induced voltage always oppose the cause which has produced it, right? Now for example, we will see this case. In this case, due to this current which is flowing in this direction, magnetic field is there, a voltage will be induced in this coil. And the direction and that induced voltage will oppose the cause which has produced it. Due to this negative sign, it indicates that the induced voltage opposes the cause which has produced it. So the direction of induced voltage here will be like this, plus minus V induced, right? So now you see the induced voltage is produced due to the magnetic field, right? Due to this varying magnetic field, and this magnetic field is basically produced due to a current, right? If there is no current in this coil, then the there will be no magnetic field, right? So basically current is the basic cause which produce this induced voltage. Right? Again I repeat, the induced voltage, see, when we place a conductor in a varying magnetic field, voltage will be induced. So we have placed this conductor in this varying magnetic field, so a voltage will be induced. Now the direction of this induced voltage will oppose the cause which has produced it. So basically this induced voltage is produced due to this varying magnetic field, and the varying magnetic field basically is produced due to this current, right? So this induced voltage opposes this current. That's why, so in this coil, the current will flow in this way, right? I induced, right? It will flow in this direction, right? That's why it opposes this current. So this is about the Faraday's second law. So remaining thing we will cover in next lecture.